We will continue with our topic on coastal protection. Right now we are going to look at coastal structures using a different type of classification. We will be looking at structures which are constructed onshore and parallel to the shoreline, structures which are constructed offshore and parallel to the shoreline, as well as structures which are constructed perpendicular and attached to the shoreline. We're going to look at the common types of structures for these three different categories, and also specifically how they interact with the coastal littoral processes. Shore parallel onshore structures are designed attached to the shoreline. They are used primarily to protect the shoreline from erosion and typically have little effect on the up coast or the down coast areas. However, the structure must be tied in properly to a non-eroding portion of the shore or protected by end walls in order to avoid flanking effect, such as what we see here in this figure. If the wall ends abruptly, then it might actually expose erodible section of the shoreline on the up coast or the down coast section to wave attack. And so for the design of shore parallel onshore structures, the main component to look at is the length of the structure, the height of the structure to avoid overtopping, the penetration depth into the seabed for scouring protection, the shape of the structure itself, and the tieback or end wall required to protect the two ends. This figure here on the left shows the scouring effect, which can happen when a vertical seawall is installed. Under the wave attack, instead of the normal erosion and accretion profile, scouring can happen right in front at the toe of the structure, so that this portion of the seabed may be subjected to erosion. This figure here on the right shows effect of flanking. If this is a coastline where only this part of the shoreline is protected, then there is a potential possibility that the up coast and the down coast may be eroded. So it is very important for the ends to be designed properly with end wall or proper tie-in. One of the most common shore parallel onshore structures is rebatment, which are made up of riprap or concrete blocks laid on a beach face, typically in a gentle profile in locations which are subjected to a mild wave climate. Another category is known as bulkheads, which are typically vertical wall with tieback into the soil, and they function more as an earth retaining structures at the seafront. Seawalls are massive structures which are designed to achieve stability by their own weight. They are built along the shoreline using stone molds or concrete structures and shaped accordingly to allow wave energy dissipation, such as a curved face or a step face. This is an example of a typical cross-section of a curved seawall with pile foundation. This figure over here shows experiment to look at how incoming wave can be deflected by a curved seawall. These figures here shows example of common toe protection design for revetment. On this slide, we are going to discuss briefly the design of penetration depth for a seawall. First and foremost, for the segment of the beach considered, typically it is assumed that the beach profile will be unchanged seaward at a water depth of 8 meters and above. Also, the beach profile will be typically unchanged landward of a slope break. For example, in this case, this is the original beach profile, and this is the mean sea level. At this point, there is a slope break whereby the beach become concave downwards. So this portion of the beach profile is typically unchanged, meaning that under erosion, let's say the eroded profile is this one, then the shape of this part, which is landward of the slope break, remains unchanged. Only this part of the beach profile has changed. By installing a seawall, we also note that the seawall has no effect on the erosion on the seaward side. So the steps of the design as described here in this list, and we will be referring mainly to this figure. First and foremost, the desired structure position will be determined, such as A over here, where this is the proposed seawall location. We will select a seaward point B where the profile is unchanged, and that should be somewhere deeper than 8 meters. So based on this location, we examine the seaward side and find a point B which preferably reflect the closure point of the beach profile, meaning that beyond this point we don't expect any profile changes due to erosion. Next, we'll have to choose a design life for our structure. In this particular case, let's presume that we're going to design for 50 years, and let's say the annual soil loss is N. That would means that in 50-year time, we expect that the shoreline will retreat from this point C to this point D. So the next thing that we're going to do is to sketch the profile DF, which is assumed to be parallel to CE. DF is parallel to CE based on the assumption that landward of the slope break, the beach profile is unchanged. And once we have done that, then we join the point F to the point B, whereby PB represent a point which is unchanged as well. So we get a new beach profile over here. So what it means right now is that we expect in 50-year time, this beach profile will be eroded to form this beach profile. And so if we desire to place our seawall over here, then we must make sure that our seawall should be penetrate below this line. And how deep it is, it will further depend on the foundation design of this particular structure. And since this structure will not have any effect on the erosion on the sea side, so we expect this beach profile to be eroded over the 50-year period and eventually form this beach profile over here. But due to the presence of this seawall on the land side, this part of the beach will not be eroded under the protection of this seawall.